we will wrap up our lessons for Chapter 1 with a lesson on density. I believe you have studied density before in middle school and probably know that density is equal to the mass of a substance or material over the volume of that substance. Often we write the equation as D is equal to M over V. And the M can be in any mass units, grams, kilograms, milligrams. Volume can be in any volume units, milliliters, liters, cubic centimeters, and this goes on and on and on. Let me tell you one thing here that's super useful. By definition, 1 milliliter is exactly equal to 1 cubic centimeter. That is a handy fact, and I suggest that you jot that down in your notebook, and perhaps that will help you remember it when you need it. Density, I believe, as you know, determines what would rise or sink in a mixture of substances. You can probably imagine that this rock would be sitting on the ground, or if it were dropped in the water, it would go to the bottom. If this is a helium balloon, it would definitely rise in the air because the density of the rock is quite high and the density of the helium balloon is less than that of the air that makes up the atmosphere of our planet. So let's do a practice example in which I'd like you to calculate the density of the metal described in this problem. At this point, please pause the video and set up your solution to this, keeping in mind one thing. In this class, it's important that you show work. In other words, the setup of how you found an answer. This is going to be true on all assessments. So get in the habit of not just grabbing a calculator, but start with what I would call the blank equation. In this case, that blank equation is D equals M over V. Then fill it in with values, and then solve, round, and put units on your answer. So I've gotten you a little bit of a head start. So pause the video now and then check back in after you've done this series of steps. Okay, I hope you paused long enough so that this didn't all jump up in your face before you were finished. I have filled in some values here. I filled in the mass right here. I filled in the volume right here. This is what the calculator shows. And you notice I have rounded my answer to 3 significant figures because my mass had 3 significant figures. My volume also has 3 sig figs, and so I am allowed, according to our rules, to only have 3 significant figures on my answer. So I'm cutting it off here, but because this is an 8, I round up to 3.30. Here are 2 more examples. Again, pause the video for a few moments. Solve these examples, remembering to start with the blank equation, then fill it in, then solve. If we look at what's going on with this first one here, we start with the equation in its given form. I've rearranged it into the form that allows me to solve directly for volume. I like to do these arrangements, algebraic rearrangements at the beginning before I start plugging numbers in. Also, the mass was in milligrams, and that is not going to be compatible with the density that is in grams. So I converted my mass from milligrams to grams before I plugged it into this equation. And then solved the problem and rounded my answer to 3 significant figures because the mass is 3 significant figures and the density is 3 significant figures. And so this would be the most correct answer. Our first task is to find the volume of the cube. I foresee that some of you are going to object that I rounded this answer to 2 significant figures. However, I must do that because my side only has 2 significant figures. And this is where sometimes this rounding stuff takes some getting used to. So once we find the volume, rearrange the equation, plug in the density and the volume, and here is your mass, again rounded to 2 significant figures. Don't let the rounding trouble you. We'll talk more about measurement throughout the course. If our measurements are not very, very exact, our answers cannot be very, very exact. That's the essence of what we're doing here with significant figures. And sadly, this volume of 2.4 centimeters is only 2 digits. And that limits the accuracy that we're allowed to keep in our answer. Here is a problem that is found on page 42 of your textbook. Determining density with water displacement is a typical lab that we would do in this class just to get used to measuring things. So let's just take a look at what's going on here. It's a little hard to see the volume of water. I believe the first volume is there and the second volume is there. So take a minute and read through this and see if you can follow what's going on. I believe you can see that the volume of the piece of rebar is equal to the volume of water that was displaced when the rebar was put into the original volume of water. And so this subtraction allowed them to find the volume of the metal. And then these values were plugged into this equation. And my answer was rounded to 2 significant figures, correctly so. I wanted to take the time in this lesson to point out the difference between accuracy and error and precision and deviation. Accuracy and error are determined relative to the right answer or the accepted value. If I were to ask you to take a shot at guessing what my dog's age is, okay? Let's say that you guess that my dog is 7 years old, and the right answer, the right age is 8, okay? Then you have an absolute error, and I can call it an error because I know what's right and wrong, of -1 year. You're off, you're low by 1 year, okay? We can calculate a percentage error by taking what we call the experimental value, in this case it's the guess, minus the accepted value divided by the accepted value multiplied by 100. And in the case of this guess for my dog's age, we would have 7 minus 8 over 8 times 100 equals, and pardon me, but I'm going to pretty much ignore the rules of significant figures here because I want to have a little more accuracy in my answer. I apologize for this. -13% error. Okay? So we were low by 13%. If we're low by 13%, our accuracy is 87%. The main thing I'm pointing out here is that we need to know the accepted value or the right answer to be able to say what our error might be. On the other hand, precision and deviation are used to evaluate the agreement when we compare a series of experimental values. In this case, there is no right answer. This might happen if you are making a measurement multiple times for a particular volume of liquid, or determining the density of a material that has only just been discovered and for which perhaps there is no accepted value. And in order to do this, we compare the values to one another. There is a way to do this mathematically. I don't think I'm going to go there right now. I am going to say if there is high precision, there's good agreement between that series of experimental values. That also means there is low deviation. On the other hand, low precision means there is poor agreement and there is high deviation. Just a couple of vocab words that need to be processed. One last thing, the very end of this chapter presents some information about temperature scales. We will never use Fahrenheit, so you do not need to know how to do Fahrenheit conversions. Celsius, however, and Kelvin will be used. The Celsius temperature scale has two reference points, 0 for the freezing point of water and 100 for the boiling point of water. The Kelvin scale also has these same two reference points, but the numbers are skewed by 273. So the freezing point of water in Kelvin is 273, and the boiling point is 373. This is the conversion between those two temperature scales. Notice one small detail here. We do have no degree sign used with Kelvin. We just call it K. So if I had a temperature of 14 degrees Celsius and I added 273, that temperature would be written as 287 kelvins.